Hello friends, welcome to the Civil Master. Today I will discuss about the second case of simply supported beam when UDL acted on a entire span of simply supported beam. So let's get started. As you can see here we have a simply supported beam of length L meter and a UDL of magnitude W kilonewton per meter acting on its entire span. There are two supports A and B and have a reaction of RA and RB. So first of all we have to find out the reactions of supports RA plus RB is equal to WL. This is our first equation. As it is a case of UDL and UDL acts on per unit length, that's why we have to multiply length with the load. Now we have to find out the individual values of RA and RB. For that we have to take a moment on the point A or a point B. So we are taking the moment at point A. Taking moment at point A. Here RA into 0, because we took the moment at A, that's why there is a 0 unit distance between the RA and point A, plus RB into L, because RB is the L meter distance apart from the A and WL load acting downwards to the beam, so minus WL into L by 2. Here we are taking WL as a load and L by 2 as a perpendicular distance from the point where moment is acting. And in case of UDL, we take that distance from the center of the UDL to the point where moment is acting. So here it is equal to 0, and from this equation we get the value of RB is equal to WL by 2. And similarly we have RA is equal to WL by 2, because the beam is symmetrical, and I have already explained the mechanism of symmetry in case of beams in my previous video. So now we have the values of all the forces acting on the beam. So let's draw the SFD of the beam as a reference line for SFD, and we are starting from the point A. We have the reaction RA at point A and the value of RA is WL by 2, so it will go upward from here by WL by 2, and it will go straight linearly up to the point B. And because of UDL acting on this beam and there is no any other load acting on this beam, so the shear force diagram will go linearly up to B, and how it is I will explain you. So here we have WL by 2 at point A and WL load acting downwards, so it will get subtracted from the RA, which is WL by 2. So at point B it will reduce up to WL by 2 minus WL, it is minus WL by 2. So at point B we have the value of shear force is minus WL by 2, and the shear force diagram will go linearly like this, and at this point we already have the reaction of RB, and the value of RB is WL by 2, and it will get added to the minus WL by 2 force. It will get added to this because RB is acting upward. So here we have minus WL by 2 plus WL by 2, it will become 0. So here it is. And the shear force diagram will look like this. Half of the portion of the triangle in above the reference line, and half of the triangle is below the reference line, and it is negative. Now I'm going to draw the bending moment diagram of this beam, and for that we have to find out the bending moments at each of the points of this beam. So there are basically 2 points A and B, but actually there is another point generating because of shear force changing its direction. Shear force changing its sign from positive to negative. So at this point it will become 0, shear force becomes 0, and when shear force changes its sign from positive to negative, the point where it changes its sign is called the point of contraflexure. It is the point of contraflexure. And at the point of contraflexure, the value of bending moment is maximum. It means the magnitude of bending moment is maximum at the point of contraflexure. So let's find out the bending moment at each of these 3 points A, B, and this point C, which is point of contraflexure. As I have already explained in my previous video that bending moment at supports is 0. So here we can write that moment at A is equal to moment at B is equal to 0. So we have to calculate the bending moment at point C. So here it is. We are going from left to right direction, and we have RA into L by 2 minus WL by 2 into L by 4. As we are taking the moment at point C, which is L by 2 distance apart from point A, so here is a perpendicular distance between A and C is L by 4. So moment at C. So here we have RA is equal to WL by 2 into L by 2 minus WL square by 8, WL square by 4 minus WL square by 8, and here we have WL square by 8. So moment at C we have WL square by 8, and it is a L square, so it is a parabolic equation. So the diagram of bending moment will go in parabolic shape, and here it is maximum at C point, which is WL square by 8. I will explain the further cases of SFD and BMD in my next videos. Thank you for watching my videos. Please like and share if you get benefit from this video, and subscribe my channel for regular learning.